while slope fields give us a way to visualize the solutions to a differential equation, they don't actually help us find those solutions. In this video, we're going to look at one particular class of differential equation for which we are often able to find the solutions. The differential equations we're going to take a look at are called separable. A first-order differential equation, y prime of t equals f of t comma y, is separable if it can be written as g of y times y prime of t equals h of t. The key thing to note here is that our function on the left, g of y, only involves our dependent variable y, while our function on the right, h of t, only involves our independent variable t. Let's think about why an equation that can be written in this form might be helpful to us. Recall that y prime of t can be rewritten as dy dt. Then in our separable differential equation, g of y times y prime of t equals h of t, we can rewrite that as g of y times dy dt equals h of t. From there, if we multiply both sides by dt, we end up with the equation g of y dy is equal to h of t dt. We can integrate both sides to get that the antiderivative of g of y dy is equal to the antiderivative of h of t dt. If both of these have analytical antiderivatives that we can find, then we have found a solution to our differential equation. Let's work through a few examples to see how separability becomes useful. Here we want to find the general solution for the separable differential equation t squared plus 1 to the third y prime of t equals t times y squared plus 4. We know that our goal is to separate this. In other words, get all the y's on the left and all the t's on the right. So we can begin by dividing both sides by t squared plus 1 to the third. We still have y's left on the right, but we can divide those out now. So we end up with y prime of t over y squared plus 4 is equal to t over t squared plus 1 to the third. We're going to rewrite y prime of t as dy dt. So we have y over y squared plus 4 dy dt is equal to t over t squared plus 1 to the third. Multiplying both sides by dt, we get that y over y squared plus 4 dy equals t over t squared plus 1 to the third dt. We can now integrate both of those. The two functions are equal, their antiderivatives must be equal, plus or minus a constant. On the left-hand side, we take the antiderivative of y over y squared plus 4 dy. We can do a u substitution. U will be y squared plus 4, so that du is 2y dy. That becomes the antiderivative of 1/2 du over u, which is 1/2 the natural log of the absolute value of u, which is, of course, 1/2 the natural log of the absolute value of y squared plus 4, plus some constant c. On the right-hand side, we have the antiderivative of t over t squared plus 1 to the third dt. That is going to give us, again doing a substitution, u is t squared plus 1, so that du is 2t dt. We are going to get 1/2 the antiderivative of du over u to the third. So we end up with 1/2 times u to the negative 2 over negative 2, which is going to give us negative 1/4 times t squared plus 1 to the negative 2 plus c. We'll label those as C1 and C2. So now we see that we have 1/2 the natural log of the absolute value of y squared plus 4 plus c1 is equal to negative 1/4, or I'm going to go ahead and put the t squared plus 1 in the denominator, so we get negative 1 over 4 times t squared plus 1 squared, plus, this should have been c2. I'm going to try to solve this for y now. So first thing I'm going to do is I'm going to notice that this is 1/2 the natural log of the absolute value of y2 plus 4 is equal to negative 1 over 4 times t squared plus 1 squared plus some constant c, where c is going to be some combination of c2 and c1. Now I'm going to multiply everything by 2, so we get the natural log of the absolute value of y squared plus 4 is equal to negative 2 over 4 times t squared plus 1 squared. I don't need to worry about multiplying the c term by 2 because 2c is just another new constant, so we'll just keep our constant there. Notice that y squared plus 4 is always positive, so I don't need the absolute value on the left-hand side. So we have the natural log of y squared plus 4 is negative 2 over 4 times t squared plus 1 squared plus c. And then we can solve that logarithmic equation. We get that e to the natural log of y squared plus 4 is equal to e to the negative 2. Oh, we can simplify the 2 and the 4, so we get negative 1 over 2 times t squared plus 1 squared plus c, giving us that y squared plus 4 equals e to the negative 1 over 2 times t squared plus 1 squared times e to the c. If we use our rules of exponents, we can split that into e to the c. Subtracting 4 from both sides, we get y squared is equal to e to the negative 1 over 2 times t squared plus 1 squared times e to the c minus 4. From here, we're going to note that e to the c is just some other constant, so we're going to rewrite that as a, so that this becomes y squared is equal to a times e to the negative 1 over 2 times t squared plus 1 squared minus 4. And so for our final answer, we take the square root of both sides and we get that the absolute value of y, so we don't have to worry about the plus or minus, is going to be the positive square root of a e to the negative 1 over 2 times t squared plus 1 squared minus 4. In this next example, let's apply what we know about separable differential equations to an initial value problem. So here we have y prime of x is equal to y times the cosine of x, and y of 0 is equal to 3. We'll start off by separating it. In other words, we'll bring the y over to the left-hand side, so we get y prime of x over y equals cosine of x. Rewriting y prime of x as dy dx, we get that 1 over y dy dx is equal to the cosine of x. And that is going to give us that dy over y is equal to the cosine of x dx. We can antidifferentiate both sides to get that the antiderivative of dy over y is equal to the antiderivative of the cosine of x dx. And that tells us then that the natural log of the absolute value of y is equal to the sine of x plus some constant c. Solving that for y, we get that e to the natural log of the absolute value of y is equal to e to the sine of x plus c. On the right, we have the absolute value of y is then going to be e to the c times e to the sine of x. e to the c, e to any number is always a positive number, so we can get rid of our absolute value, and so we end up with that y is equal to, using the trick we used in the previous example, we're going to write e to the c as some constant a, so we get y equals a times e to the sine of x. Now we'll apply our initial condition. Y of 0 is a times e to the sine of 0, which is equal to 3. E to the sine of 0 is e to the 0, which we know is 1. So we see that a must be equal to 3. And so our solution to this is that y is equal to 3e to the sine x. We'll pause for a second from doing examples to talk about some vocabulary. In the previous two examples, we were able to solve both of them so that we got y as what we call an explicit function of the independent variable. In other words, we were able to write our final answer in the form y equals some function of either x or t. That's not always the case. Sometimes we need to leave our solution in what's called the implicit form. So an implicit solution is going to be a relation between x and y, or perhaps t and y, whatever the independent variable is that we're using, that satisfies the differential equation, but y can't be isolated on one side of the equation. Let's take a look at an example that has to be written in its implicit form. Let's take a look at what happens when we try to solve this initial value problem. We have dy dx is equal to x times 1 plus y over y, and the initial condition that y of 0 is equal to 1. We're going to separate this, so we'll multiply both sides by y over y plus 1 to get y over y plus 1 times dy dx equals x. Multiplying by dx, we get y over y 1 plus y dy is equal to x dx. Now we can antidifferentiate both sides. So let's look at the antiderivative of y over 1 plus y dy. That's the same as y over y plus 1. The reason I'm rewriting that is because if I divide y plus 1 into y, I get 1 and then minus 1. So that means that this is the same as y over y plus 1 is the same thing as 1 minus 1 over y plus 1. So this antiderivative becomes the antiderivative of 1 minus 1 over y plus 1 dy, which, antidifferentiating that, we're going to get y minus the natural log of the absolute value of y plus 1. And we have some constant c there. Now let's look at the right-hand side. This one's easier. The antiderivative of x dx is x squared over 2 plus c. So what we end up with is that y minus the natural log of the absolute value of y plus 1 plus some constant c1 is equal to x squared over 2 plus some constant c2. We can combine the two constants together to get that y minus the natural log of the absolute value of y plus 1 is equal to x squared over 2 plus c. Now we'll apply our initial condition, which was that y of 0 is equal to 1. So we'll replace all of our x's with zeros and all of our y's with 1s, and that will help us figure out what c is. So we get 1 minus the natural log of the absolute value of 1 plus 1 is 2 is equal to 0 over 2 plus c. So c must be 1 minus the natural log of 2. Rewriting all of this then gives us that y minus the natural log of the absolute value of y plus 1 is equal to x squared over 2 plus 1 minus the natural log of 2. There is no way to solve that algebraically to get y by itself. So we have to leave it in this what's called implicit form, and this is our final implicit solution. So summarizing what we've learned, if we can rewrite our differential equation so that we can get the dependent variable on the left-hand side and the independent variable on the right-hand side, in other words, we can separate it, then we can attempt to apply integration techniques in order to come up with a solution to that differential equation.